Good day, everybody, and welcome to our fifth version of the Elmarco Talks. This is where we invite industrial and academic experts to come and present their research related to electrospinning. Today, we are talking about a very important topic to the current state, is about shaping water and energy technologies by electrospinning. And I want to say, before we get into the discussion, something about some future webinars that we'll have, which is going to be Elmarco Talks, talking about our incubator program. An incubator program is where we can help together to develop some nanofiber products, and we'll be talking about that on February 20th, sorry. And then we have one more scheduled also for March 13th, and we'll talk about advanced bio-based and circular materials adapted for electrospinning together with Arkema. But today I want to introduce the shaping of water and energy technologies by electrospinning, and this is going to be presented by Professor Angela Zhang. She has a quite impressive CV. Professor Zhang is the head of section in water technology and processes in the Department of Environmental and Resource Engineering at the Technical University of Denmark. And Angela holds a bachelor degree in polymer materials, a master's degree in physics, a PhD degree in chemical and biomolecular engineering, and an executive MBA degree in management of technology. So what we were going to do, maybe I should introduce myself as well. I'm Josh Manasco, and my colleague Katka Rubishkova. We're going to be moderating the talk today. And what we're going to do next is discuss just a little bit about Elmarco before we get into this specific talk.
So as usual, it's my pleasure to remind you or repeat some facts about our company. So we are a global leader of supplying, designing, assembling, and supplying technology called Nanospider. We are located in a beautiful country, Czech Republic, middle of Europe, where everything is here, is R&D, production, assembly, everything is located in one place, and we work with partners to help us to provide the sales globally. We are more than 20 years in the market. We have a lot of patents and hundreds of machines installed. So how does the technology look like? What is the principle? So basically, we are utilizing the method of electrospinning. We are working with the needle-free technology-based, where we are using wire as a spinning electrode. We work from the solution, so polymer needs to be dissolved first to form the solution, which is coming on the top of the wire, and the fibers are generated from the surface of this wire and are coming onto the moving substrate against the collecting electrode, which is again the wire. And by this method, we are forming a uniform, let's say, nano coating or nano layer, which is continuously coming on the surface of this moving substrate. We work from roll to roll production. It means on one side, you have the empty roll of whatever paper, non-woven substrate. And in the end, you have the product coated with the nanofibers. This is a portfolio of our machineries that we are supplying. So top line are demonstrating the laboratory scale equipments or pilot scale equipments. But our core business is based on supplying really fully integrated industrial scale technology, where the Nanospider is just part of it. The rest forms the peripherals, which are important. So we are delivering, installing, and training this full scale, let's say, technology for making nanofibers. As the last time, I like to mention a couple of words about our newest product, which is half-meter, let's say, pilot line, where we are introducing 2 additional electrodes. So now instead of 1 electrode, we have in total 3 electrodes in a spinning chamber, where the biggest benefits is to increase the throughput of production. So this is rather kind of compact, small, let's say, pilot scale product where you can make reasonable quantity of the product. At the same time, we are introducing kind of bonus selection of different collectors, where one of them is the rotating electrode, which offers the production of aligned fibers, and the other one is endless belt, which increases the portfolio of used substrate, because nowadays you can, with this electrode, you can work with less conductive substrate. And the nanofiber application, of course, the benefits of nanofibers are broad. First of all, of course, the air filtration is still the top, let's say, the applications that where we have the most of our customers of ours are in this segment. But very rapidly coming liquid filtration and medical segment. About medicine, we talked about last time many times. Acoustic, energy, and performance apparel. But today, we're going to cover two application segment, which is the liquid filtration. And I think that's very important because of the importance of water resources nowadays on this planet is very important. And the energy, which is also quite interesting and very current topic. Josh?
Yeah, so quick bookkeeping is, if you're going to ask questions, please feel free. Don't put them in the chat, but put them in the Q&A box so that we make sure we get those. And after Angela is finished with her discussion, then we'll come back to the questions and answer those as they come to us. So just please make sure to do that. So without further ado, if Angela, if you could share your screen, and we can begin your talk. Thank you very much.
Thank you very much for having me here. So today I would like to introduce our research and innovation in the water and the energy technology by electron spinning. And first of all, I want to introduce our sections. And I'm the head of section for water technology and processes. And we are at the Technical University of Denmark. As you can see from the list of the members of the section, we are 34 people, from the young PhD students to scientists and all the way to senior professors. And our focus is the treatment of water and also the residual streams in urban, industrial, and also agriculture settings. And we are very proud because our technology pathway design are based on the understanding of different domain water. For instance, wastewater, groundwater, and seawater. And we not only do basic research, but we also make the transition from the knowledge, the science, to the applications to impact the society and also technology advancements. We research area, we have microbiotechnology and advanced material and membrane. I will talk about it today. And also we focus on the micropollutant removal and resource recovery. So let me see here. It's if I take my head of section head off, and I'm also leading a research at the DTU. It's called Advanced Material and Membrane for Water and Energy Technologies. And for us, we have two strong legs in terms of application. One is on the water, and the other one is on the energy. For instance, we work with the wastewater treatments, and we focus on not only removal of micropollutants, but also we focus on the resource recovery. Nowadays, wastewater treatment plants like a platform for nutrition, for the energy recovery. And also we now quite focus on the water purification. And this is not only for drinking water, but also for the ultra pure water production, for green hydrogen production, and also for the chip manufacturing, for instance. And once we have the pure water, we can also make a connection to the energy sectors. For instance, if you have ultra pure water, you can put it into electrolyzer to produce green hydrogen. And if you have hydrogen, And then you can also use fuel cells to convert chemical energy in the fuels into electricity. And among all those technologies, and we also have a very strong hold at the department about the assessment of absolute sustainability. So we have the ability to not only focus on the economics, the cost, but also the environmental impact, the sustainability as a whole. So we can explore the design space between the sustainability, cost, and functionality. And once we have those need for application, we often have the ability to go to the root, especially for the material synthesis and also the structuring. And then we can tailor the functionality and process to fit into the certain application. For structuring, we are very proud we have the capability to do electron spinning. So here you can see in our lab, we have 2 electron spinning next to each other. And we have needle-based electron spinning, and that's for students to design in the smaller scale. But our goal is once we design the materials and found we have the proof of concept, we always make a transition to Elmarco equipment and to see the upscaling potentials. And we're also very proud to have the Elmarco air conditioning unit here as well, can precisely control the temperature and humidity. And here's the trick, is that we are able to use the control of the temperature and relative humidity to control the nanofiber orientation at the molecular level. And here you will see we can tailor the orientation of molecular chains to boost the physical properties of a single nanofiber and eventually a nanofiber membrane as a whole. We also have the capability to combine the material synthesis. That's expand our portfolio. For instance, here is an example of polymer nanofibers. So by electron spinning and also the probe treatment, we can convert nonwoven into a woven nanofiber membranes. And we also can activate the surface of nanofibers and grow nanoparticles on top of that. Here is metal organic framework. They have a potential to absorb certain ions and pollutants in the liquid phase or in the air phase, in the air. And with this, we can expand the filtration with a certain resource recovery. In terms of energy application, and often that requires a continuous pathway for electrons. That's why we can carbonize these nanofibers and produce carbon nanofiber-based electrode. So here, you have enormous amount of surface area and also provide the active site to trigger the reactions. And last but not the least is ceramic nanofibers. We combine electron spinning with sol-gel synthesis. Here is a peroxide nanofiber ceramic materials. They can conduct ions. We use it in solid oxide fuel cell or solid oxide electrolyzers. So now I would like to zoom out from those materials, but also focus on the application. So beyond the best available technology, first in energy, we focus on fuel cells and also electrolysis for green hydrogen production. And what we do is that we combine the catalyst, ion exchange resin, and also the electron spinning technique to construct 3-dimensional nanofiber electrode that can facilitate mass transport, also activate the catalyst for the reaction. And for the water side, we know forward osmosis has tremendous potential for the up concentration of a certain liquid. And here we work together with Aquaporin, the company in Denmark, where we use electron spinning to make a substrate for them to coat the aquaporin protein for the forward osmosis membranes. And we also realize that actually there are a tremendous amount of waste heat nowadays. And that's why we also focus on the thermal-driven water purification. Here is membrane distillation, and they use waste heat as a driving force to produce ultra-pure water. Often the most challenging part is the membrane itself. So it needs to be hydrophobic and also anti-fouling. So we use electron spinning to create special shapes to boost the hydrophobicity. And on top of that, we also make catalytic membrane reactors. And we put enzymatic catalyst and also photocatalyst on top of nanofibers. So that can combine the catalyst reaction and with membrane filtration. So now I'm going to talk about these two cases first. So for that, the driving force for us to go in to that direction is because of the environmental challenge, particularly is contaminants of emerging concerns. We call it CECs. They are toxic to human beings, and they also have a long-term effect on the ecosystem. They're often very small in size and low in concentration. That's why conventional water treatment infrastructure nowadays in the countries is not sufficient to remove those contaminants. Particularly, for instance, pharmaceuticals. And we, in Denmark, we have quite a lot of pharmaceutical companies as well. And worldwide, there is a challenge. They found the pharmaceuticals in the wastewater, in the aqua system. So how do we address these concerns? And conventional, there are some techniques for the CEC elimination. For instance, carbon absorption, a sludge, or advanced oxidization process. But recently, there is a trend. More and more people are looking at the membrane process. So membrane is by size exclusion, and they use it to remove the contaminants and to ensure the water discharge are used, they are not contain CECs. However, when we look at those membrane process, and they are not elimination of the contaminants, they are just to up-concentrate the CEC in their waste stream. So eventually, we still need to go to extra miles to see how can we remove those contaminants. And one of the technology pathway we are exploring is by using enzymatic reactors, because those enzymes is one of the most efficient biocatalysts to degrade compounds. And also by working with concentrated contaminants in the membrane waste stream, that also boosts efficiency in our design. So we look into the flexible enzyme ceramic nanofiber membrane for the transformation of emerging pollutants. What we want to do here is to have the ceramic membrane with the enzyme on top that can combine the filtration and degradation of the contaminants. So how did we do it? We first do electron spinning, use Elmarco, and also we do the calcination to convert the polymer membrane into silicon dioxide nanofibers. And then we will functionalize it to make some functional groups to make, and also put enzyme on top. So there will be not only physical absorption, but also covalent bonds to ensure the enzymes stay on top. And then we will pass it through the filtration system and to evaluate the performance. So first we can see those ceramic membranes are flexible. So that's quite different from our common sense about ceramic. They're rigid and quite bulky as well. Here is like a piece of cloth, and they are ceramic, and there's a dimension about 200 to 300 nanometers, and the thickness about 50 micrometers. And then we functionalize those nanofibers, and we also put the enzyme. So by confocal microscope, you can see those grains, the shine light indicates enzyme presence in our nanofibers. Then we put it into test. So put in the filtration with contaminates, those CECs, like diclofenac, those kind of pharmaceutical compounds we found frequently in our water in Denmark. And then we will do the analysis. And when we pass those water through, and we found the depletion efficiency of those nanofiber membrane can reach up to 95%. So 95% of those compounds can be removed and degraded. And also we operate into 3 paths. So the enzyme, the stability are fairly good. And then the other advantage of this ceramic membrane is that if enzyme has are losing their capacity, we can always reuse the ceramic membrane. That's an advantage compared to the polymer membrane. So as a short summary of this one, then you can see the lactase enzyme immobilized on the membranes. We can really reach the filtration and also the degradation of compounds. Another one that we look at is plastic management as well. So plastic is quite abundant in our daily life, but often they can break into small pieces, especially now we're talking about microplastic in many streams and even in air. So how can we deal with this plastic waste? One way is to the separation. So you can use membrane to take microplastic out of the water stream, but we're still facing the other way. What do we do with it? You can burn it or you can discharge it, but what we are going to do is to upcycle it. To upcycle means a process of converting materials into a new materials, has economic values or increase functionality. So what we did here is to put photocatalyst on top of fiber membranes. Then we can not only capture those microplastic, but also can convert into a value-added compound. So here we use photocatalyst. We synthesize our high entropy catalyst, and those catalysts has very high efficiency in terms of photoactivities, and also they can absorb not only UV light, but actually solar light. So we can have solar light driven reactions as well. And we put it into the membrane, so structure in the way that we can capture those microplastic, and then we trigger the reaction at the same time. So how we do it? Always start with electron spinning. So this is a conventional nanofiber membranes, and with pore size about around 1 micrometers, like microfiltration range. And then we do the in situ growth of those catalysts. So you can see after those reactions, all the fibers are roughened by our high entropy catalyst. So then we put it into our small reactors and to evaluate the performance. We also have the solar light simulator to shine the light on top of that. So you can see our small device, and this is a microplastic we use in our experiment is a PLA. And then you can see with the membrane design. So instead of just conventionally, you just put the catalyst into a batch process and stir it. And you can see with the membrane, you can capture the microplastic while triggering the reaction. This membrane reactor has much higher efficiency. And we can convert this polymer microplastic into acetic acid and have a much higher, almost 6 times higher yield rate compared to the powder form. And also compare with other catalysts, you can see the efficiency with high entropy ones actually reaches the highest efficiency. And also in terms of the selectivity, and here you can see with our catalyst, with our nanofiber membrane, and then they can reach 73% of selectivity in terms of the acetic acid productions. So short catch up on this one, we have synthesized the catalyst, and those catalysts are grown on top of nanofiber, so we get a catalytic nanofiber membrane. And that one can capture the microplastic from the water phase, and at the same time, powered by solar light, they can trigger the upcycling of polymer into value-added chemicals. So now enough for the water, and also I want to jump to the energy part. And here we often talk about the hydrogen economy. Now, especially with reduction in the cost of sustainable energy, now people more and more look at the hydrogen economy. So with electrolysis powered by wind turbines or solar light, then they can produce hydrogen, and those hydrogen can be utilized for the fuel cells to convert chemical energy into electricity. So our work is to use electron spinning to structure especially the electrode part. I think this is a work I have, that's when I started electron spinning research about 10 years ago when I was a postdoc at Vanderbilt University in the United States, where at the first time I invented a three-dimensional nanofiber electrode that combined the catalyst with the naphthalene as air conduction phase, and then we electron spin into a nanofiber electrode that we see very nice structure, as you can see here. And each fiber are roughened by the catalyst. This is a platinum carbon catalyst. With this kind of design, we can reach 40% reduction in the platinum consumption with even higher performance than the conventional ones. So with this, we actually opened the entire field about electron spinning for energy device, especially for electrochemical reactions. Now at the DTU, we are working towards another type of fuel cell that is a high temperature PEM fuel cell, operate at around 160 degrees Celsius. So here we look at the self-standing flexible nanofiber electrode. So what we did is that we put a metal organic framework, and into the polymer, we do electron spinning, and then we do the carbonization. By the galvanic replacement, we can exchange cobalt with platinum. So we created this platinum cobalt catalyst. And those electrodes are very, very flexible. So you can see those power structures and those electrodes that has carbonized as well. And then they can conduct the electrons, and the catalyst can trigger the reaction. And by those, we can produce the electrode by roll-to-roll production, cut into pieces, and then hot press on the membrane. So we can make the MEA in a much convenient ways as compared to industrial practice. And you can also see in the high temperature, around 160 degrees Celsius, underflow of hydrogen and oxygen, and the performance also shows enhancement in terms of the power density. So this is a brief introduction about our energy part. We are still working on the new electrode design for the electrolysis as well. And hopefully next time, when we file the patent, we will be able to also show you the result of the electrolyzer part. But at the end, I see all the result I have present is not myself. Actually, I have a brilliant team and also collaborator with me here at the DTU. And we also very grateful for the financial support from the foundation in Denmark, in Europe, and also from the companies as well. So with that, I want to thank you all for having me here, and I will be happy to answer your questions. Thanks.
All right. Thank you so much, Angela.
Thank
you for the very interesting talk. There's one question I was going to just start. We'll start with some specific questions, then maybe some broader questions towards the end of the question section. So just keep asking your questions. But there's one that's coming from Peter. It's a very interesting talk, Angela. Have you tried electrospinning on any other components of the fuel cell, such as a proton membrane or GDL, or as a bipolar plate coating?
Yeah, very good question. Actually, we try electron spin on the gas diffusion layer because it's conductive, it's quite nice. I agree that this is really nice. If you can just directly coat on the gas diffusion layer and then you hot press with membrane to make the MEA, that brilliant approach. But we also tried on the ion exchange membrane because of the conductivity issue. So we didn't manage to do so. But just now I heard that you have those new electrode, and I hope we will have the opportunity to try it. The substrates that can work with less conductive substrate. We hope if there is new design in the instrument, that would also facilitate, the connection between the electrode and the membranes.
Yeah, what Angela's talking about is our endless belt that we had mentioned briefly about being able to spin on substrates that aren't so conductive, or some more difficult ones. I have a very specific question about your enzymatic CEC removal. You said that it's a very flexible membrane. Do you guys have to put some support layers there to run your test, or how does that work with your test? And then on top of that, you said something about reusing. I saw that there was some small drop in performance after 3 cycles.
Yeah.
Can you recycle these, or let's say reactivate these, or reuse these in any way? Like, can you get into more detail?
Yeah, of course, I would love to. So for your first questions, and for the membrane, for the ceramic membrane, it's freestanding. So we can use it as it is. We don't need the substrate. We normally put it into our cells for the filtrations. And then, of course, the cell itself also provides the integrity of the filtration system. For your second question, the slight decrease in terms of the efficiency after 3 rounds. First is quite and you see this kind of stress test, and we put a lot of contaminant in the feed water, just to to see the decrease over reasonable time. So in reality, it will be much lower concentration. And second is that decrease actually is not due to the nanofiber; it's due to the enzyme. So that's I think the part we hope that we'll have more technology coming up in the future for this application to have more robust enzyme. But our thought is that what dictate the lifetime of enzymatic membrane reactors is not it's not membrane, at least in our case, it's enzyme. But if it's polymer membranes with enzyme that that's majority of the research or publications about, then once enzyme is die, and then often it's very difficult to recycle the polymer membrane substrate. That's why we come with the ceramic ones. You can burn, or you can use some chemicals to remove it, and then we can re-implement or re-impregnate the enzyme on top of that. So from the sustainability point of view, it's also kind of a reuse of the ceramic membranes.
Thank you. I have also actually a question related to that, to the ceramic membrane. I made some notes. So you said that the application area would be pharma industry for treating the water. Let's say the old tests you did, I suppose they were on a kind of small scale. How about upscaling it? Do you have any plans for future, or do you see that actually coming? Do you have any partner that you would go with especially for this application?
Yeah, thank you for asking that question. I think one thing is that what we did is kind of a proof of concept, and we do see the impact. We see the potential in this, but of course we cannot work all the way to the end. We need to partner with the knowledge providers, the instrument provider, and the end user to develop it together. So that's why it's also a call for partnership. I hope people in the audience, or that someone are looking into this solution as well. We can work together.
Another question from audience. Have you investigated other photocatalysts, maybe also for hydrogen production? Observed any degradation of the polymer and the interface?
Yes, that's a very good. Actually, we are now working on the green hydrogen production with our nanofiber electrodes, and we see the boost of the performance quite dramatically. For the degradation part, I think is very tricky. So in a sense that especially polymer, if it's alkaline electrolyzer, then in a very high pH value of electrolyte, the polymer does have very, very tough time. So that's why now we are looking at replacement of those polymer materials. So that's the work we are going on at DTU at the moment.
There's one more question from the audience from Mandeep, asking about the polymer issue such as PAN that uses like DMF, for instance, also for carbon production. It produces HCN gases, so it's more about the polymer solvent issues and sustainability. Do you have any comments about?
I'm very happy. The audience also. That's also one of the things we hope to address, because you know, the solvent we are using in the electron spinning, not only for environmental impact, but also they are quite expensive. So in a sense, to upscale the process, I do see the value of recycled solvent. I know some of the collaborators I know of, they are working on that, and to see whether they can recycle the solvents. That is definitely will boost the overall sustainability.
And I had one more question about the microplastics with the catalyst. When you did that test, did you put the membrane in there as is, like a membrane, or did you break it apart into pieces, or what did you do during those testing exactly for the catalytic degradation of the polymer?
Yep. So we especially focus on the microplastic in water phase, because those particles, they can escape the conventional water treatment, and because of the small size. So that's why we especially bought the plastic, and then we crack it into a small piece to simulate the microplastic, which is below 1 millimeters and around the micrometers range. So that's the particle we put it into our feed water for the filtration and the catalytic conversion.
Another from audience. So what do you think about the core shell nanofibers? So have you tried to use them in a membrane technology, the core shells?
Yes, actually we did a core shell electron spinning, and then we did the carbonization to make a binary catalyst for zinc air batteries. And so we have the paper published in small, and then we really see the kind of very unique structures. So if you have the core is one catalyst and the shell is another catalyst, so you can combine two reactions in one fibers. It's really fascinating to see what we can do with the electron spinning. But of course, core shell electron spinning, I hope that I will see in the future there is industrial scale production for core shell electron spinning as well. That I think if that can from the equipment or the hardware side, if that can have a more advanced equipment, then of course our ideas and our innovation will also have the future for commercialization.
Yeah. So these are kind of more general questions. So how could you imagine to accelerate, like actually the electrospinning research and innovation, especially on the university platform? What you can say about that?
Yes, I think I also did the research for my EMBA study. I especially look at deep technology innovation, the role of the university. And for deep tech, it's kind of application inspired research and innovation. So especially, for instance, what I presented today is water and energy. They have the potential to fundamentally change the way we clean water, produce energy, or cure disease. But they do need the innovation that is very different from what we used to in the daily life. But if I look at the innovation model, often we see is quite linear. For instance, scientists in the lab, they have some ideas and they create the proof of concept. And once they found, oh, it can go to the higher TRL level, and they hand it to the company or the entrepreneur and see whether there is a potential for upscaling. So then there is a decouple of the idea phase as an initial step, and there's a development to the evaluation part. So what I think the most efficient way for us to do innovation, and especially to minimize the gap between research and commercialization, is to, at the very beginning, when you shape the idea, when you try to see where is a crucial aspect for us to work on as a university, is to have the consortium, not only the researcher, but also the technology provider and end user. If we can have the consortium like this from the very beginning of the research, they can already give you the input of what they want or what is most impactful area for you to work on. Then the researchers can have a better input and then combine those elements into our research design. And also, those innovation is not linear. It's not we can get it better and better just like one go, but sometimes it's circular. So we have idea, we try, it might sometimes fail, but we learn from the failure, and then we can come back and redesign and revalidate. So I think those are circular mindset as the innovation part, and also the collaboration across discipline and across sectors. That's very crucial for future innovation.
Thank you.
We agree. It's very important to have those end users and those people that have pains that they need to solve, that you can focus your research.
Mm-hmm. And actually, we will have a next webinar dedicated to incubator.
Yeah.
We can kind of put the details, and we are kind of gathering the ideas.
We're trying to do something like that ourselves, so we agree with that wholeheartedly.
That's why I really appreciate the webinar you're organizing here. I can see the past webinar you organize, not only researchers, but also the companies, and they come together and we have a discussion together. That's where I think the best idea can win and inspire each other.
Thank you.
We have a couple of questions coming in from the audience. So one question is, do you think that functionalizing the nanofibers will affect the porosity of the scaffolds?
Yes, certainly. But I don't think it will be dramatically change. Often what we do is that the growth of the functionalization of the fibers is at it's very thin around the fibers. So it will change the porosity, often reduce the porosity, but also will not sacrifice the porous structures of nanofibers. Sometimes I often see that the porosity is at a higher level compared to what is needed in our application. So often we need to compress it to reduce the pore size, especially, for instance, for air or for liquid filtration that are functional with size exclusion. And then functionalization of the fibers do contribute to that direction.
Reducing the pore size by functionalizing the materials.
Yes, you can, but not. I don't think it's a large extent. We can see like 20, 30%, but not more than that, at least in our case.
Yeah. Another question from audience, Kibron is asking, have you observed any leaching of the coated or encapsulated functional materials from the nanofibers during the tests? If you
That's
can
a good
comment
question.
there.
I think from our experience, we haven't observed it. The reason is because, for instance, for enzyme, and it's by covalent bonding. For our catalyst, we do in situ growth. So for the fuel cells, what we did is to put catalyst together with polymers, and then we do the electron spinning as a composite nanofibers. So all those cases, they have very strong bonding between the fibers, the polymer substrate or ceramic with the active catalyst. So during our filtration, we didn't see the leaching part.
And a second question from the same person was, you mentioned that water purification is also important for the water electrolysis for green hydrogen production. Have you managed so far to produce a more stable electrode or PEM, AEM in the electrolysis stack?
We actually, the water purification part is on the water side. So the reason to do that is from an electrolyzer manufacturing perspective, they want very high quality water. So to not trigger the irreversible damage to the electrolyzer, we need to meet a minimum ASTM type 2 water requirement. That means the resistivity is larger than 1 megohms. That's very, very pure water we are talking about. So we especially focus on how we can convert the unconventional water, like seawater, wastewater, stormwater, and into ultra pure water. And then we can feed to the electrolyzer. Of course, we also see nothing is perfect. So there are always some ions or purity will go through the membrane and then come to the electrolyzer. So that's why our research also to focus on what the impact of those very, very low amount of impurity on the long-term performance of the electrolyzer. So that's why we combine our expertise in water and the energy together.
There's another question related to the water purification, specifically from the textile wastewater segment. So do you purify the textile wastewater with the nanofibers membrane? Have you done any tests on that?
Like removing dyes, for example, is one of the.
Actually, right now we are on a project, especially for mainly for textile, but for laundry wastewater. So similar sector, but they also have, for instance, microplastic and the CECs and also dyes. For instance, if you wash the colorful garments, then you will also have the dyes in your wastewater. So we are working on those kind of membranes and also try use a functionalized membrane to remove the dyes.
And somebody else asking about the method, what method would be used to scale the calcination and functionalization processes?
It's kind of interesting.
Yeah, it is. I think that's probably the most challenge I see in this route. And I think electron spinning, for instance, Elmarco did a fabulous job to upscale the electron spinning. So we are now worried about getting a large scale production of nanofibers. And then on top of that, for the functionalization, there is a transition, like how we can upscale that chemical reaction side. For us, those kind of in situ growth, we use relatively easy chemical synthesis. For instance, use water-based and relative mild temperature as well. But for the carbonization, it does have some of the the challenges on that. How we can upscale that carbonization process and with the affordable price at the end for such carbonized nanofibers. That's indeed a challenge.
And one other question from the audience is, have you used the nanofiber structure along with catalytic coating for air purification?
Air purification, not yet. But we do have the collaboration within the EU projects. We are not the expert on the air purification, but we are the one that designed for instance, the catalyst on top or the material on top of the nanofiber. So those materials can have selective absorptions of the chemicals in the air.
There's a repeatable question about the purification of a textile wastewater again. So which membrane do you suggest to purify the textile wastewater? I guess this question is coming directly from the textile industry. So
Yes.
that's why it's so important for them.
Yeah, I think textile the industry. I think the treatment need to be like in different step, especially for the pre-treatment. And then in that case, often the textile wastewater has a fairly high temperature, and also a lot of quite high TOC as well. So often we are now looking at is a ceramic membrane for the treatment. And at the end, you will have the polishing step, especially if you want to remove the dyes, very small moleculars. And that one that we now exploring is to functionalize the membrane with our material absorbent. So as the last polishing step, then you can selectively take those dyes out. So I would suggest a ceramic-based membrane for this.
Thank you.
And somebody's asking about biomaterials for artificial organs. Do you see any application in that field?
That's a very big field. I think the first couple of the papers I read about electron spinning actually is from tissue engineering, especially because it mimics the tissue structures of human beings, and especially we look quite a lot of cell growth, especially very fascinating papers about the stem cell growth on top of nanofiber structures. I think those are really interesting, and I can see the rise in terms of publications and also innovation in that field as well.
So we're coming to the end, so I'm going to ask you a very broad question and let you discuss it. What about the future research directions at DTU regarding water and energy nexus?
I think that we have a very strong hold in our department and research group is on the understanding of water and also energy, especially the connections between those two. So right now, what our focus is to understand the challenge in the water sectors, especially focus on the micro pollutants and for instance, PFAS, the pesticides, pharmaceutical compounds. How can we remove those when they are so small and so low in concentration, but so toxic in the long term? The other one we look at is about resource recovery. So when you have those membrane filtration to take the pollutants out and you create a concentrate, those concentrate actually give the opportunity for us to recover the nutrients, the chemicals, and also to degrade the pollutants. So that's why combine the membrane technology with a catalyst, then we will be able to not only produce clean water, but also to have the resource recovery on the concentrate side. And then especially through the hydrogen or the power to X sectors, the pure water we can produce and that connection to the electrolysis of water and produce green hydrogen. I think that's also very, very important. That's our focus in the future as well, to see how we can design the electrolyzer as well to make it more efficient when the water is not, never is perfect.
There's another question from audience asking you for valuable inputs on how to clean the drinking water, let's say from arsenic, or how to make a drinking water free of arsenic and lead.
Lead and arsenic.
Yeah, lead and arsenic free drinking water.
Yeah. My research is not particular for arsenic removal, but I do know that especially when we work with metal organic frameworks, and they have special design for such a moth to selectively absorb the arsenic in water. But of course, then the concentration, low concentration is often a challenge to make scalable and affordable. So that's at least I think we have materials that can do it. And then the next step is to make cheaper and also scalable.
And then maybe a question related to all that, and it's very general again. So do you see actually potential or how to commercialize these electrospin membranes in water technology? So that's all related to water, which is quite interesting and important. So the question is more broad, and so if you can comment that about the commercialization of such a membrane, so what that would mean.
Yeah, I think often the electron spinning, they can make fascinating structures and also bring very unique functionality. But often when we go to the innovation and commercialization, people often ask, then what about the cost? So we always need to consider the cost of the processing and also material synthesis side. So I think the future potential is that we need to look at the value creation by having additional, electron bond structures. And that value has to be high enough to cover the cost of the processing side. That's why we especially look at, for instance, not only water treatment, but resource recovery and the connection to the energy. When at the end of your membrane, the other side, you can create a valuable water or valuable chemicals, and they can address the devastating environmental impact. Then you have the room for us to accommodate more advanced electron spinning and synthesis.
And maybe the final last question is somebody's asking if they can come work for your group. So I think you've been very successful, and it's been a very interesting talk.
Very, very welcome. We have open positions, so welcome to apply.
I would highlight this last slide where it has the contact information for Angela, her email address and phone number. So I think that that's a perfect end to the talk. Thank you, Angela, very much for your time and your detailed answers, and very interesting work, and very, very interesting for this time, for sure. So.
Yeah, thank you very much. Thank you for having me, and thank you all the audience for your very interesting question.
And then for the remaining part of the audience, please stay with us also for the next time. We are follow us on our website where you have more detailed information about next coming talk, which is coming next month. So please stay with us. Okay, goodbye.
Thank you,
everybody.
Bye.